All right, guys, welcome back, Honors Chem. Today we are going to learn a little bit about Le Chatelier's principle. And it's a really useful principle to use for equilibrium to determine which way the equilibrium will shift when something happens to that equilibrium, some kind of a stress. So it's something that we use a lot, especially when you get into more complicated ice charts. It will help you understand how to set up that ice chart. Okay, in 1888, French chemist Henri Louis Le Chatelier discovered that there are ways to control equilibria to make reactions more productive. And we do that all the time, especially in a chemical engineering industrial setting. We're always trying to make things as efficient as possible because that's money on the bottom line of those companies. He proposed what is now called Le Chatelier's principle. If a stress is applied to a system at equilibrium, a system shifts in a direction that will alleviate or relieve that stress. A stress is any kind of change in a system at an equilibrium that upsets that system. So when we are talking about stresses in an equilibrium system, those stresses are usually the following. We can change concentration of either a reactant or a product. We can add some or remove some. We can change the volume. We can either make that volume bigger or smaller. We can change the pressure of the system. We can either increase or decrease the pressure, and we can change the temperature. We can either increase or decrease that temperature. All of those are stresses that an equilibrium system will have to shift to alleviate or to relieve the stress. Okay? So I want you to think of, and we've talked about this a little bit before, I want you to think of an old-fashioned, like Greco-Roman or like way old-fashioned Babylonian balance. So if we have a balance sitting up on a table and we have pan number 1 and we have pan number 2, we're going to pretend like the one on the left is the reactants and the one on the right is the products. And we're going to do everything that we can to keep them even. Okay, we're going to keep them even and keep them balanced. So if anything upsets the reactants or the products, we have to do something to make them even again. Okay, so here we go. If I increase the nitrogen or hydrogen in this reaction, this is, by the way, this is the reaction of nitrogen getting together with hydrogen to make ammonia plus heat. This is what we use. This is the Haber process. And this is the process that we use to fix nitrogen so that we can use it for fertilizer. Okay, so if I'm increasing nitrogen or hydrogen, I'm essentially putting more stuff on this reactants end, making the reactants end really heavy. That makes the product end go way up, which means I've got to find a way to make the product end heavier to get it back even. So to make the product end heavier, that means I need to make more products. So I'm going to shift right. Notice the products are on the right side of the equation. I'm going to shift right to make more products to get that balance even again. So we would call this shifting right. Okay. All right. Let's look at the next one. So if I decrease, so I'm taking ammonia out of the process, taking that out, boom, gone. Doesn't that make the product side really, really light? boom, that product side's going to go way up. So that means that I've got to make more products for it to get heavier to balance out the reactants that I have. So once again, I'm going to shift to the right to make more products. Okay, so let's look at this next one. I'm going to increase the temperature. Increase that temperature. Now, notice that the heat is on the product side. So that means we've got a, yes, exothermic reaction. That is releasing a lot of heat. So if I want to think of that heat as a product here, okay, if it's on the left-hand side, it's an endothermic reaction, and it's going to be a reactant. So it's the same as putting a bunch of extra stuff on that product pan. So that's going to make that product pan really, really heavy. I need to make the reactant side heavier to rebalance things out. So I'm going to shift left to make more reactants to get that to be even again. Okay, let's look at pressure. What does pressure do to a system? So when we look at pressure, we have to really look at the amount of moles of gas on each side. So here I'm going to increase the pressure. So I'm pushing things closer together. So if I'm pushing things closer together, they're going to want it to occupy as little space as possible. So let's look at the number of moles on each side of gas. Only gases affect this. So I've got 1 mole of gas here, and I've got 3 moles of gas here. So my reactant side, I have 4 moles of gas. On my product side, I have 2 moles of gas. So what is going to occupy the smaller space? 4 or 2? 2 occupies less space than 4 moles of gas. So if I'm increasing that pressure, I'm definitely going to want to be smaller. So I'm going to shift to the right to make less moles of gas to occupy less space. Okay, what happens if I add a catalyst? Now, a catalyst just speeds up the reaction. If a reaction is at equilibrium, it means it's going both ways at the same rate. So does it change the reaction if I'm going both ways at the same rate? No, it just makes it faster. It doesn't change the reaction at all. It just, or that equilibrium concentration, it just gets us to equilibrium faster. That's it. So add a catalyst is no shift whatsoever. It just gets us there faster. Okay, so let's look at some of the things that will actually have us shift to the right. So if I add a reactant, that makes that reactant side really heavy. So I need to balance it out by making more product by shifting to the right. If I remove a product, it causes the reactant or the product side to be really light. So I've got to make it heavier again to balance out the reactants. So I've got to shift right to make more product. Now on number 3 here, if I shift to the left, one way I can do that is by removing a reactant. It makes our reactant side really light. So I need to shift to the reactant side to make it heavier again to balance it out. Or I can add a product which makes the product side really heavy, which means I have to make more reactants to rebalance that out again. Okay? Now, if we're looking at heat, if I have a exothermic reaction in number 1, if I have an exothermic reaction, it's going to act as a product. So if I raise that temperature, it's the same as creating that product side, making it really heavy. So I'm going to shift to the left to make that even again, with the reactant side. If I lower the temperature, it's the same thing as removing a product. So I'm going to shift to the right to make more products, to make more heat. Okay? If I have an endothermic reaction, though, if I raise that temperature, it's the same as making the reactant side heavy. So I'm going to shift to the right and make more products to use up that extra heat. If I lower the temperature, though, on an endothermic reaction, I need to generate more heat. It's the same thing as removing a reactant. And so I'm going to shift to the left to make more reactants. Okay? So these are great little notes for you. So let's do some practice. Example 8. How would each of the following changes affect the equilibrium position, either shift right, left, or no shift, used to produce methanol from carbon monoxide and hydrogen? So we've got our product, we've got our reactants, and we've got our products. Notice this is exothermic. So heat is going to be like a product here. So let's see, if I add CO2 to this system, it's going to make my reactant side really heavy. So I'm going to need to shift right to make more products. So I'm going to shift right. Okay. What about cooling the system? Cooling the system is the same as taking this heat and taking it away. So it's the same as removing a product. So I'm going to make that product side really light. So I'm going to need to make more products to get it to even out. So I'm going to shift right. Okay, what happens if I add a catalyst? Do you guys remember? Adding a catalyst just gets us to equilibrium faster. It doesn't shift. So this is going to be no shift. Just gets us there faster. What if I take methanol out of the system? That's going away from the system. That makes my product side really light. So I'm going to have to make more products to make it even again. So I'm going to shift right. What about volume? What do I need to look at for the volume? That's right. I need to look at, did you guys say number of moles of gas? So let's look at the number of moles on my reactant side. I've got 3 moles of gas on my reactant side. And on my product side, I have 1 mole of gas. So if I decrease that volume, I'm pushing those molecules close together. They're going to want to take up as little volume as possible. So what takes up smaller volume? 3 or 1? 1 does. So I'm going to shift right. Okay, how'd you do on those? All right, let's look at number 9. I want you guys to do these on your own and then compare notes with me, okay? So take a minute, look at this. You guys ready to try, to check? Okay, so I've got ethylene reacting with hydrogen to form ethane, okay? How would I regulate the temperature of this equilibrium in order to accomplish the following? So I want to increase the yield of ethane. So I want to shift this right. So I'm going to do this with heat. How can I shift it right? Did you guess remove the heat? Yeah, I've got to decrease the temperature or remove heat. Remove the heat. Okay. How about decrease the concentration of ethylene? Okay, so I want to take the ethylene and I want to decrease the concentration. So that means I want to shift right? If I want to decrease the concentration of ethylene, so I'm going to remove the heat so that it will shift right. So I am going to decrease that temperature or remove the heat. Okay? What if I want to increase the amount of hydrogen in the system? Okay, so I want to increase this. So I actually want this to shift to the left if I want to increase my hydrogen concentration. So I am going to do what I need to do to shift it left. I'm going to increase the temperature. Okay, how'd you do on those? All right, here's another thing, some more practice for us. Okay, I've got nitrogen dioxide or dinitrogen tetraoxide, which is that brown, gray, mucky stuff that we see in our inversions, going back and forth with nitrogen dioxide, which is emitted from our cars when we drive. So this is the equilibrium that we have, especially we can see it when we have our inversions going on in the valley. So the delta H here is a positive 92 kilojoules. That means I have to add that heat in. So actually the delta H here is a reactant. Okay, this takes energy to do it. So we're going to put it on the reactant side. If it was negative, it would be exothermic and the delta H would be on the right-hand side. Okay, so we're going to go through each of these stresses and we're going to see what it does to the concentrations of each of these things. And we are going to see if the equilibrium shifts right or left and see if it changes our equilibrium constant. Now remember, the only thing that changes equilibrium constants is the temperature change. Okay, that's the only thing that changes those constants. So if I increase my dinitrogen tetraoxide, of course that's going to increase. So that is going to make things shift to the right. So I'm going to shift right. So if I shift right, what does that do to my nitrogen dioxide concentration? It also is going to increase. Okay. Does my KQ change? No, because I have not changed the temperature. So that is a no change. Okay. So I want you to go through these really quickly and see if you can predict what's going on with these. Okay. All right. Nitrogen dioxide is increased. So that's going to shift everything left. Nitrogen dioxide is going to increase, and nitrogen, initially it's going to increase, but eventually it will go down, just like this eventually will go down eventually. Okay, so it's going to shift left. There's going to be no change at all in the KQ. Temperature is increased. So temperature is acting as a reactant here. So if I increase that temperature, I'm going to shift right. How'd you do on that one? So if I shift right, that means my concentration of nitrogen dioxide is going to go up and my concentration of dinitrogen tetraoxide is going to go down. So if that happens, and remember, this is a temperature change. Remember, we have products over reactants. That means my equilibrium constant is actually going to get bigger because I have more products now and fewer reactants. So my equilibrium constant is going to get bigger at a higher temperature. All right, nitrogen dioxide is decreased. So I'm going to just, anything that's changed, I'm going to just kind of X out. So if dinitrogen tetraoxide is decreased, that means I'm going to shift left. So that means that my nitrogen dioxide is going to go down. And I haven't changed the temperature, so I'm going to have no change in my KEQ. How about nitrogen dioxide being decreased? So I'm just going to put an X here because we're not. So if my nitrogen dioxide is decreased, I'm going to have to shift right to make more product. So I'm going to shift right. That means my dinitrogen tetroxide concentration is going to go down. And I'm not changing the temperature at all. So I am not going to have a shift on my equilibrium constant. Okay, that will not provide a shift there. Okay, and there goes my computer once again. Hopefully it will not take too much longer for it to think. Okay, now let's think about if the temperature is decreased. That means we're taking heat out. So it's like removing a reactant. So if we're removing a reactant, it's going to shift left. Okay. So on our temperature being decreased, it's going to shift left. And that means our concentration of dinitrogen tetroxide is going to go up, and our concentration of nitrogen dioxide is going to go down. So our concentration of our products are going down, and our concentration of our reactants is going up. So that means our equilibrium constant is going to go down. Okay? Pressure. Let's talk about pressure really quick. So if I look at pressure, I have 1 mole of gas for my reactants, and I have 2 moles of gas for my products. Okay, so if pressure is increased, I want to take as little volume up as possible. So which is going to take up less volume, 1 mole of gas or 2 moles of gas? 1 mole is. So I'm going to shift to the left. I'm going to shift left towards the dinitrogen tetroxide. So my dinitrogen tetroxide product or concentration is going to go up, and my nitrogen dioxide concentration is going to go down. My equilibrium constant, though, because I have no change in temperature, is going to stay the same. So let's fill those in. So my dinitrogen tetroxide will go up, my nitrogen dioxide will go down, shifting to the left, no change here. Okay, and this is going to be no change here. Oh my, I can't win, can I? All right. No change here. Temperature is decreased, so we said we would shift to the left. That means our concentration of dinitrogen tetroxide would go up, our nitrogen dioxide would go down, and our KEQ value would go down because we would have less products. How did you do on those? Okay, so let's see. Oh, pressure being decreased. So that means we're going to expand, which means we would actually be able to have more moles. So we're going to shift to the right. So if we shift right here, our concentration of nitrogen dioxide is going to go up. Our concentration of dinitrogen tetroxide is going to go down, and there's going to be no change on our KEQ. All right. Last but not least, there's this one. Take a minute, see if you can figure it out. Now, I've got a positive 98 kilojoules. So, and it looks like it's written as part of the equation. So I'm going to consider this exothermic. Okay, so I have hydrochloric acid reacting with oxygen, making water, 2 chlorines, and heat. So this is an exothermic reaction. Okay, so see what you can do. You guys ready to check? All right, I'm going to just X out the hydrochloric acid. So if hydrochloric acid is increased, we're going to shift to the right. And because we're not changing the temperature, we are going to have no change on our KEQ. Okay, so if we shift right, our oxygen concentration is going to go down. Okay, our water concentration is going to go up. Right? Let's do number or letter B. Water is increased, so I'm going to just X that out. Now, we're not changing the temperature, so our KEQ is not going to change. If water is increased, that's a product. So we're going to actually shift left to make more reactants. So that means our concentration of hydrochloric acid is going to go up and our concentration of oxygen is going to go up. Okay, oxygen's increased. So we're not going to worry about the oxygen. Because we're not changing the temperature, we are not changing the equilibrium constant. So oxygen is a reactant. So if it's increased, that means we're going to make more products. We're going to shift right. Okay, and if we shift right, that means our hydrochloric acid is going to go down. It means our concentration of oxygen is also going to go down. Okay, temperature is increased. So temperature is a product here. So if I increase the temperature, we're going to shift left to make more reactants. We're going to shift left. Now, if we make more reactants, that means our equilibrium constant is going to go down because our concentration of our products is going to go down and our concentration of our reactants is going to go up. So our reactants are oxygen there and hydrochloric acid, and our product, water, concentration is going to go down. How did you do on that one? All right, pressure. Let's look at our moles of our gas here. We've got 5 moles of gas over on our reactant side, and we've got 4 moles of gas on our product side. So if pressure is increased, we're smushing things together. We want it to be smaller. So 4 moles of gas is easier to accommodate. So we're going to shift right. But we are not changing the temperature, so there's going to be no change here. Okay, so that means shifting right, our hydrochloric acid concentration is going to go down, our water concentration is going to go up, and our oxygen concentration is going to go down. Okay, how'd you do on that one? All right, let's shift a little bit. Our pressure is decreased. So it's going to be the opposite of what we just did. We are expanding, so we can actually create more space. We're not going to have any change. We're going to shift to favor our reactants. So our concentration of hydrochloric acid is going to go up, and our concentration of oxygen is going to go up. But our concentration of water is going to go down. Okay? Temperature is decreased. So let's look at this. It's the same as removing temperature. So it makes our products lighter. So we're going to shift right. Okay, so we're going to shift right, which means that we are going to have more products. So that means our equilibrium constant is going to go up. It means our reactants concentrations are going to go down, and it means our product concentrations are going to go up. Okay, water is decreased. So water is a product. So it's the same as taking a product away. So we're going to shift right to make more products, but we are not changing the temperature. So we're not going to get any change in our equilibrium constant. So that means our products are going to go up and our reactants, oxygen and hydrochloric acid are going to go down. Oh my gosh, my brain is not working. Okay, so there is predictions of how things will shift just using the Chateliers, just using that balance of if something's disturbed, which way is it going to rock that balance, and how do you get it back even again? I hope this is helpful to you. If you have any questions, please email me or come and see me after school or before school or during flex. Talk to you later. Bye.